Namaste, my dear friends. Welcome to CS with RS. Today, we are going to discuss a very important topic, functional and non-functional requirements. In system design interviews, the questions are pretty one-liners. Let's say you're asked to design a URL shortening service or a key value pair store, or let's say design a TikTok or YouTube, etc. As you can see, not much information is provided to you. Now, at this point of time, the first and the foremost thing that you should do is spend a couple of minutes and finalize the functional aspects of the system and the non-functional aspects of the system. In that way, these requirements will become the center point around which you can design the entire system. Let's better understand with an example. Let's say you're asked to design a unique ID generator. Now, you may end up designing a system, but that system works well only on one server. But the interviewer is expecting you to design this service which is in a distributed environment. I mean, it's working on multiple servers or cluster of servers. And let's say you design a system that works well for 10 TPS of traffic. Okay, but the interviewer wants you to design system that supports 100 TPS of traffic. So in order to finalize these requirements, you should spend a couple of minutes with the interviewer and list them down. So let's get started. Let's first understand what are functional requirements. So functional requirements basically are the core aspects of the system, the core task that a system will perform. We can say that, okay, our system performs these, let's say 1, 2, 3, 4 tasks. And if the system is able to perform these tasks well, we can say that the system is working as it is intended to work. So what are the components of a functional requirements? Basically, first is the input. Input is what data as a user we are feeding into the system. Let's say we are presented with a login form. So our username and our password, it becomes the input to our system. Next come process. Process is basically the APIs that we write in the system, that we code into the system. In this example, logging in, the authentication part becomes the process of the system. Okay, so the system accepts this process, accepts the input, username, password, cross checks it with the database and performs necessary action. The third one is the output. Output is basically what the system is performing after accepting the input and processing our input. So in our case, if the username password matches, the user is taken to the home page or the dashboard page, and if there is a password mismatch, the authentication fails. So the user is presented with an appropriate message that your credentials do not match. The next one is behavior. So what do we mean by behavior? Let's say you log into your net banking, and as you must have noticed, if you leave the site idle for let's say 5 minutes, 6 minutes, the system automatically locks you off and a message is shown on the screen that the user is signed off due to inactivity. Please log in to continue. So this basically is an example of behavior of the system. So let's now understand functional requirements better by taking examples of some commonly asked interview questions in system design. Let's start with a unique ID generator. So first of all, what is the purpose of unique ID generator? As the name suggests, it's basically a system that is generating unique identifiers. And where these unique identifiers are required, let's say we have an e-commerce website where we need to generate a unique order ID for each order that is being placed. So that's one use case of this system. Another one is, let's say we have a tiny URL system where basically our long URL is shortened into a short form version of this URL. So their unique IDs are required. Okay, so what will be the functional requirements of this system? Number one, the system should be able to generate a unique ID. This ID should be generated in less than 10 milliseconds. Otherwise, it affects the performance. If the latency is high, the user experience will be very bad. And this ID must be collision free. What do we understand by collision? Duplicacy. Let's say our system works on 5 servers and server number 3 generated this unique ID 123. So this ID should not be generated previously by any of the 4 servers. System shall provide the user with configuration formats. And what are these configuration formats? Let's say we want our IDs only to be numeric. 1, 2, 3, 4, 5, only digits should be present, or we may require an alphanumeric format ABC 1, 2, 3, or a UUID, or it could be a snowflake style unique identifier that was developed by Twitter. I mean, it has multiple things. It has a sign bit, it has machine IDs, it has unique identifier, timestamp, and multiple things combined to create one ID. Next, we can take an example of a URL shortening system. So, what does a URL shortening system do? Let's take an example. You must have noticed, let's say if you get any SMS, let's say from Flipkart, and they also send you with a link to click and take some action. So that link is not the complete lengthy URL, okay, starting from HTTPS, then colon, then www.flipkart.com, then /abc/xyz and /whatnot. No, that's not the case. It could be, let's say, a tiny URL. Tiny URL is basically a service that provides this URL shortening service. Okay, so it could be like tiny URL dot 123 dot /123 abc, whatever. So once you click on this tiny URL, basically the tiny URL system maps this shorter version of URL with the longer version of URL, and you are redirected internally in the browser to the longer format of URL and taking you to the Flipkart site. So that's an example of what a tiny URL system does. So what will be the functional requirements of the system? Number one, the system should accept the long URL and create a shorter version of this URL. And once the user clicks on the short version of URL, the system shall redirect user to its original URL. This mapping between shorter and longer version of the URL must be stored in the system, and the system should be able to perform some analytics like the number of times a specific URL was clicked, the timing of that click, okay, the IP address from where the URL was hit. We must have a feature of TTL, time to live. We cannot just allow this mapping to be stored indefinitely in our system. Let's say we have 30 days or 15 days or maybe minutes, maybe hours, depending upon the user case. And the system shall expose some APIs like post API to shorten the URL. It accepts the longer format of URL and maps it into a shorter version. A get endpoint where the user hits the shorter endpoint, okay, and the system redirects it internally to the longer format of the URL. And it could have a get method by name analytics where the shorter version of URL is presented and the user is presented with the dashboard. Let's take another example of a key value store. As the name suggests, a key value store is a system where we are able to store a unique key corresponding to a value in that system. A common example is Redis. So what will be the functional requirements of this system? The user should be able to store data. We will have an endpoint put where we are passing the key value pair which is saved in the system. Now in order to fetch the data corresponding to a key, our system will have a get endpoint as well. Now let's say a user decides to update the value corresponding to a key. So we will have a put method that will allow user to update the value. If the user decides to delete this key value pair, we will have a delete method in the system. Now there could be millions of users, millions of entries in a system, so we cannot allow this data to persist indefinitely in a system. So user will also be provided with the option to set a TTL, how long the user wants these key value pairs to exist in the system. And let's say a user tries to fetch a key which got deleted or expired in the system, so a system should send an appropriate error message to the user as well. So these are basically some of the functional requirements for this key value pair system. Now I hope you must be very clear with what functional requirements are. So now let's jump to non-functional requirements. So functional requirements basically show us what the system does, whereas non-functional requirements shows us how the system works under certain conditions. Over a course of time, when a system will run, it will face multiple situations. Situations like there could be a scenario of data partition, or the network disconnection between servers, or there is a peak traffic. Let's say our system is able to support a traffic of 20 TPS, but let's say it's an e-commerce system and the sale starts at 12 p.m. So all of a sudden traffic moved up to 60 TPS, 80 TPS from 20-25 TPS of regular traffic. So under these situations, and there could be multiple other situations as well, how the system performs, these basically are set criteria set by non-functional requirements. So non-functional requirements basically list down a set of criteria or standards that a system should meet in order for it to work efficiently. Let's find out what these criteria are. Availability. So what does availability means? Availability is basically for how long our system is operational. Let's take an example. One day we have 24 hours. So in this 24 hours, let's say our system is up and running for 23 hours and 30 minutes and it has a downtime of 30 minutes. So what does it mean? If we perform the basic mathematics, we could find out that our system is operational or available rather for 98% of the time, and for 2% it was down, it was non-functional. So what are the key aspects of availability? Like how can we say that the system is available? Number one is uptime. Uptime is basically the time for which our system was up and it was working, as compared to the downtime, the time for which our system was down and it was not working, it was not available. And this uptime is commonly represented as percentage, like 99.99%, 99.999%, and this percentage is in the digits of 9. You can say 4 nines, 5 nines, 6 nines, 7 9. And as you can see on your screen, there is a table of multiple nines, maybe 4 nines, 5 nines, 6 nines, 7 9, the time duration for which the system is up and the time duration for which the system is down. And all these cloud service providers like AWS or Google Cloud or Microsoft Azure present the downtime or the uptime that their system provides. You can check it out on their websites. Another key aspect of availability is redundancy. So redundancy, as the name suggests, means duplicacy. Let's understand it with an example. We have a database. On one hand, we decide to keep this database only on single server. What happens if the server goes down? Maybe due to network failure or maybe due to hardware failure. The entire CRUD operations that our system was performing, it collapses. It's not able to perform that. It might result in our entire system going down. On the other hand, we decide to keep these databases in 3 servers. Now, even if one server goes down, our system still have 2 servers to connect to. Let's say 2 servers go down, our system still have at least 1 server to connect to. So this will result in our application still keeping up, still performing. Although it may introduce some latency, but that's okay. The next aspect of availability is failover mechanism. Failover means, let's say we have MySQL DB, we have set up as primary and secondary. Now what happens when the primary system goes down? The system will automatically switch to the secondary MySQL DB. So this results in the system operating as usual without any downtime or without any issue arising due to the failure of primary server. Good. Next is load balancing. Load balancing means the load. Load means here the number of requests which are coming to our system is evenly distributed across all the servers. Let's say we have a cluster of 4 servers and we have 100 requests coming in. So we will have a load balancer and all our servers will be behind this load balancer. So each request will first come to the load balancer, and load balancer has its algorithms. Like the commonly used algorithm is round robin algorithm. So this algorithm will result in each of the server getting approximately 25 requests. Another aspect is geographical distribution. What do we mean by geographical distribution? Let's take an example of AWS. AWS has database infrastructure set up, internet data centers in India. It has IDC in Singapore, Europe, US. So by geographical distribution, it means we store our infrastructure in like servers, our cache, our database, load balancers, gateways, and what all components that we use, not just in one region. Let's say we are in India, so of course our choice will be India to reduce latency, but we also make a backup and store it in Singapore, so that let's say there is a natural calamity. Let's say we have a data center in Delhi and Delhi gets rocked by earthquake, just an assumption, and it has resulted in that data center going down. Now it may take n number of days for it to come up. And if we have only our infra set up in one region, that may result in our entire application going down for those number of days. But if we have a backup here there in Singapore, our system can easily switch from India data center to Singapore data center. So despite having the entire IDC data center of one region going down, our system will still keep functioning. Although there will be some latency, but again, some millisecond of latency is far better than the system not working for n number of days. The last aspect of availability is maintenance and monitoring. So what do we mean by maintenance? Let's take an example. You want to perform any database migration. So how will you perform that migration? We will obviously have to take a downtime. And what is the correct time to take the downtime? Well, it depends upon the time where the traffic is least in our system. Let's say our major number of users are Indians. So the ideal downtime is midnight. IRCTC is a classic example. It has a downtime of every day from 11:40 p.m. to 12:20 a.m. And let's say if we have our user base primarily in US, so the time difference is around 12 hours. So we can have a downtime in the afternoon time, maybe 12 o'clock in the afternoon, maybe 1 a.m. or 1 p.m. or 2 p.m. And what do we mean by monitoring? Monitoring is basically we set up alerts. Like in AWS, we have a lot of alerts like when the CPU utilization increases beyond the threshold. Let's say we expect 75% to be the maximum CPU utilization. And if that utilization gets crossed, we have alerts in the system. Same goes for hard disk usage. Same goes for memory or bandwidth. So we can set up multiple kind of alerts in the system so that if there is any anomaly in the system, something abnormal is taking place, we get alerted before any major eruption takes place. So that's about availability. So next type of non-functional requirement is reliability. So what do we mean by reliability? Reliable, as the word goes, it means we can trust. So reliability means our system is trustworthy, right? We can trust that the system will keep functioning over a period of time, no matter what kind of adverse situation arises. With passing time, our system will be able to handle it and respond correspondingly and ensure that the system is up and running. And the biggest benefit of a reliable system is user experience. Now, how does reliability is achieved in a system? Number one is consistency. What do we mean by consistency? Let's say we have MySQL DB and we have stored it in 3 servers. We are using a cluster. Now, consistency means the data in the entire cluster means all the 3 servers remain consistent. Let's say I make a write. ID is 10, primary ID, and I made an entry. Let's say name is Rahul Soni. So that ID and name data has entered server number 2. So that server number 2 data will be replicated at both server number 1 and server number 3. So let's say my read query, the moment I perform a write, I have an immediate read query and that read query goes to server number 3. So that server number 3 is able to send back the data that okay, ID number 10 corresponds to name Rahul Soni. So this is what consistency means. Next is fault tolerance. So what is fault tolerance? Fault, any issue that comes into the system. Tolerance means a system is able to tolerate it without crushing down the system. So all the errors that are happening in the system is able to handle it gracefully without affecting the user performance. Next is error handling. So what do we mean by error handling? On a very practical note, with the passing of time, no matter how best we create a system, there will be scenarios when errors will be introduced into the system. So the system should be able to respond properly. By response, what do I mean? Response means system should be able to log these errors properly and take appropriate action, ensuring that the system does not get crashed in the process. Next is predictable performance. So what do we exactly mean by predictable performance? It means the performance of the system, both in case of regular traffic and peak traffic, remains predictable. Right? We can say how the system is performing in regular traffic. Let's take an example of e-commerce website. Regular, we are getting 20 TPS of traffic, and let's say we have a sale at 12 p.m. afternoon, and the peak traffic grows to 60, 70, 80 TPS. So we can be sure that our system, since it's reliable, It handles both the regular traffic and the peak traffic normally. There is not any abnormality in the system just because the traffic has increased from 20 to 60. The system is able to handle such an increase in traffic. The last one is graceful degradation. So what do we mean by graceful degradation? There will be scenarios where part of the system stops working, it crashes. Okay, let's say we have a microservice architecture of the system and one of the service gets crashed. Let's say in e-commerce application we have a service that is taking care of order details, the past orders of the user. That service gets crashed. So now the system should be able to handle this gracefully. Okay, a common example is the use of circuit breakers. So all the requests that were going through this service that is not responding, okay, the entire cluster is not responding, not just one single server. So that circuit will be opened since the service is not responding, and user will be presented with an error message, a graceful error handling, what we call it. But this will result in part of the system not being responsive, but the other part of the system will keep working as it is. So this is what graceful degradation means. The next kind of non-functional requirement is scalability. Scalability means it's the ability of a system to increase its resources or to decrease its resources on the basis of the traffic that the system is experiencing. The system is able to add, let's say, a new servers into its own cluster, okay, because the traffic has increased. Like in our example, when the sale happened in an e-commerce website from 20 to 60 TPS, the traffic increased threefolds. So now if we were previously able to serve 20 TPS of traffic with, let's say, a cluster of 3 servers, now in order to serve 60 TPS of traffic, we need additional 6 more servers. So if you take an example of AWS provides this feature of auto scaling, where you can configure, let's say, when the traffic will increase, the resource utilization will increase. For 20 TPS of traffic, if 30-40% CPU utilization was normal, so when the traffic will reach to 60 TPS, the CPU utilization will definitely cross 75-80%. So we can set there, if the utilization of CPU is beyond 70 or 75%, another server will become a part of the cluster. In that way, the system will auto scale itself, and from a cluster of 3 servers, the system will scale up to 9 servers just to handle this traffic. And what happens when the traffic of, say, let's say at 1 PM, after 1 hour, the traffic comes down. So from 60 TPS, again, the traffic is falling down back to 20 TPS. So the additional 6 servers that were added, we will again have a feature of auto descaling, that when the CPU utilization reaches down to, let's say, 20%, traffic is less, so that CPU will be removed from the cluster. So when the traffic after 1 hour will restore back to 20 TPS, we again will have a cluster of only 3 servers which were previously part of the cluster. Now there are 2 kinds of scalings that happen. One is vertical scaling, another one is horizontal scaling. What do we mean by vertical scaling? We have one server. Let's say we have a server with RAM of 16 GB, okay, and we have a hard disk of 1 TB and 1 core, CPU core. So vertical scaling means we can increase the capacity of this server itself. Let's say from 1 core we increased it to 2 cores or 3 cores. From 16 GB of RAM, we have increased it to, let's say, 64 GB of RAM. From 1 TB of hard disk, we have increased it to 2 TB of hard disk. So we are increasing the capacity of the existing server. This is what vertical scaling means. And horizontal scaling, like the example of the e-commerce website, we were able to add new servers into the cluster. So this is what vertical scaling means. There are some key concepts in scalability. Number one is elasticity. Elasticity, as I gave an example, is the ability of a system to automatically either scale up or scale down on the basis of traffic. Next is sharding. Sharding basically means we are dividing our data. Let's say we have a data of 100 entries, okay, and we have our server in 4 clusters. Let's say we have set up our server database in 4 servers. So sharding basically divides this data set of 100 entries into, let's say, approximately 25 entries each in the respective server. So this is what sharding means. Next is caching. Caching, as we know, is basically used to store the frequently used data. So we don't have to make a call to database, and we are able to serve the request by caching. Caching is faster than database because cache data is stored in memory, whereas the database data is stored in hard disk. So it increases the call to database, increases the latency of the call. Next is load balancing. As we discussed previously, load balancing is distributing the load equally amongst the servers. And the last one is asynchronous processing. So like a common example, synchronous processing means the REST APIs that we are creating. It's a synchronous call. Request will go and the response will come. So this both the trip basically means a synchronous call. You're waiting for the response. And asynchronous call means we have sent a request and we have forgotten. The system is working as usual, like in the case of message queue. The next non-functional requirement is maintainability. So maintainability basically means we as engineers, how feasible it is for us to maintain the system over a course of time. By maintaining, I mean, if there is any issue in the system, how easily we can repair that issue. If we want to add any enhancement into the system, how easy it is for us to improve our system. And if we want to make any update, any modification, how feasible it is for us to update the system. So how do we maintain, or how do we, increase the maintainability of a system? Number one, modularity. Modularity basically means, let's take an example. Few years back, monolithic applications were the norm. Like we have the entire application in one code repo. But sometimes from now, microservice architecture has become quite popular. The reason behind this is modularity. Okay, we have, let's say, 10 functionality of a system that is present in one code. If we try to maybe repair or modify one aspect of the system, and if something happens, there are good amount of chances that it may affect other 3 or other 4 part of the system. So work has to be done on one entire system, that one entire monolithic application. But in case of microservice architecture, even if one service is not functioning properly, we know that the issue is present in only one service. The remaining 9 services keep functioning as it is. The next aspect of maintainability is readability and documentation. By readability, I mean the code that we write as developers should be written in such a manner, knowing that 5 years, 6 years down the line, if any new engineer looks into our code, he or she is easily able to grasp, to understand what exactly were we trying to do. And how we can do that by following clean code practices. And talking about documentation, so it's very important that we document. Like we have a readme file in our project where we basically write the steps. First of all, like what the service is doing in the entire architecture, where does our system fall, what is the purpose, what are the inputs to this service, what are the output to the service, what are the reason behind developing this service. And we should also mention these steps, let's say especially the local setup steps. What are we actually trying to do? Like how can we set this service up in our local system? What are the dependencies? Next is automation tools like CI/CD, continuous integration and continuous deployment. We can use tools like GitHub Action for continuous integration or Spinnaker pipeline for continuous deployment. So all these automated tools increase the maintainability of the system. Next is backward compatibility. Let's say we have an API which has a request payload of 10 fields, and we decide after 2 years that we now need to update the payload to 12 fields. Now when we update our API, it's not possible that the entire user base that was previously using our API for 2 years all of a sudden within maybe few hours or few days is able to switch to the updated API. So we should ensure that despite having these updates, our previous user base is able to use the previous API along with the updated API that we have created in the system. We should give them this time. And how do we do that? By creating versioning. Version 1 for the previous API and version 2 for the new updated API. And one more thing is separation of concerns. Like we did give an example of microservice architecture. Like the concerns basically here represents the features of the service that we have. One could be authentication and authorization. Another one could be card management. Third one could be past order details. Fourth one could be placing new orders. Fifth one could be payment related. So all these concerns should be separated. Like they must have a respective service for each one of them rather than having all of them under one roof, under one monolithic application. So things like these basically increases the maintainability of our system. It helps us to maintain our system quite easily, and that process of maintenance becomes quite feasible for us. Okay, the next kind of non-functional requirement is fault tolerance. So as we have previously have a brief discussion on fault tolerance, it's basically some over the course of time, our system will experience some faults. Faults are basically the issues that arise in the system. So our system should be able to handle those faults. Like that's what tolerate those faults. The performance of the system will definitely reduce, but the system will keep functioning. Okay, with reduced performance of course, but that reduction in performance is far better as compared to the entire system going down. So this is what fault tolerance means. Like take an example, we have a cluster of three servers for one microservice that is related to, let's say, authentication and authorization. Now one of the server goes down, so that does not mean that any user authentication request which is coming into the system will be rejected. Why? Because the system still has two servers who are up and running. Okay, so again performance will be lowered. Let's say we are receiving a traffic of 10 TPS for authentication and authorization. With three servers we were able to respond back to the user, let's say in 200 milliseconds. Now with only with three servers we were able to respond for that authorization request in 200 milliseconds. Now since we have one server going down, we have only two servers, so we will be able to respond, let's say, in 300 milliseconds. But still it is far better than giving let's say a 404 or some other error message, maybe 500 server unreachable error to the user. It's still far better. Latency is far better. So how do we maintain fault tolerance? Number one is redundancy. Okay, let's say we have a database. Let's take another example of database. So instead of storing database in one server, we store it in three servers. So the data is redundant here, a copy of each entry. Like I gave an example previously in our discussion that if I make an entry in the database with ID 10 named Rahul Soni, it goes to server number 2. So that is basically redundant now. It has been replicated both to server number 1 and server number 3. So now all these three servers have ID 10 with name Rahul Soni. So even if one server goes down, server 1 and server 2 will have this data. Next one is replication. As I mentioned, the data is replicated. Entry went to, the write request went to server number 2, but it got replicated to both server number 1 and server number 3. Another way of achieving fault tolerance is failover mechanism. Let's take this very example. We have three servers, 1, 2, 3 for MySQL DB, and server number 2, it went out. It got some hardware issue, so it's not responding. So the system should be able to divert the remaining request only to server number 1 and server number 3. How will that happen? We will have a load balancer behind these three servers. So the load balancer keeps having a health check of each server. It sends out requests to all the three servers, and it notices that server number 2 is not responding. So it will mark that server number 2 is not responsive in its list, and only server number 1 and server number 3 are responsive. So all the future read and write requests that will come to the load balancer will be sent only to server number 1 and here to server number 3. Server number 2 in the middle will not be sent any further request. Graceful degradation is another feature of fault tolerance. As we discussed previously, if any part of the system is going down, system is able to handle it gracefully. If order history service is not working, not an issue. Server will send a response to the user that please try later, but the remaining service will keep on running. Another thing is error detection and recovery. Like we discussed just a while back, if one service is not responding, system, we have circuit breakers in place. So the circuit breaker is able to detect that okay, this service is not responding, so the end user is reverted with a proper message rather than with an abnormal message, any failure message. So one last type of non-functional requirement is performance. So basically what does performance means? Performance is basically how much time my system is taking to respond back to a user. This is my system, this is my user placed an action in my system, let's say hit an API. So how much time my system is taking to respond back to the user. And note, this performance of the system is basically calculated under expected workload. So what does expected workload means? How do we determine expected workload? Let's say we are having a regular traffic of 20 TPS. So under 20 TPS of traffic, how much time my system is taking to respond back to the user? In that way, we can calculate the performance of a system for 20 TPS of traffic. Let's say I have an endpoint X. For 20 TPS of traffic, how much time my system is taking? Let's say I've configured my JMeter. I've configured my JMeter to send 20 TPS of traffic. I'm doing some performance testing. That's how we are able to come up to this number. Okay. I have deployed my services on my integration environment, and now I'm performing the load testing. I've created a load of 20 TPS, and that 20 TPS of load, in that load testing, I can figure out how much time my system is taking to send back the response to this specific user. And if I have to make any tweak, if I'm not satisfied with the result, I will make any tweak in my system. And let's say it is taking 200 milliseconds and I expect it to revert back in 100 milliseconds. So I'll definitely look into the way my system is built. I'll make some modification, and once I can reach that 100 or 110 millisecond of response time, I can be sure that okay, my performance time is 110 milliseconds for 20 TPS of traffic. Now the key aspects of performance is the response time that we have just discussed. Throughput is basically number of transactions the system can handle per second. Maybe the system is able to handle, let's say, 20 API calls per second, maybe 40, maybe 50, depends upon the system. Latency is basically the time delay between the request and the response. Resource usage is basically how much resource my system is using. Let's say we had a load testing of at 20 TPS. We can see that okay, my system is taking this much CPU, this much memory, this much bandwidth, and we can calculate it both under normal traffic, let's say of 20 TPS in an example, and we can increase the load to 60 TPS, and then we can check how much resources our system is consuming at 60 TPS of traffic. And one more thing is concurrency. Concurrency is ability of a system to handle multiple requests concurrently. Like as I mentioned, 20 transactions per second, and these TPS traffic could include authorization, it could include placing orders, maybe fetching pass details, viewing product details, viewing card details, etc. Alright guys, this brings us to the end of this video. Let's quickly summarize. Functional requirements are basically what a system should do, and non-functional requirements are how a system should perform and behave. Now, if you found this video informative and useful, please like this video and subscribe to our channel for future videos like these. Also, you can drop a comment below and let us know your opinion on this information that we have discussed today. Thank you so much for watching. See you guys in the next video. Namaste.